I'm sure you're all familiar when a screen is drawn. So so generally, like a frame is drawn 60 times a second. So that means like, so if monitor starts like drawing each pixel and it goes along, and it's drawing every pixel, and then once it like reaches the end of a line, it goes to the next line and the next line, and it just keeps going this, and it draws all the way down, and it will do this in about 16 milliseconds. And then it'll draw the next line, 16 milliseconds, draw the next line, 16 milliseconds, and it'll keep drawing, and it'll be 60 frames per second. And the way that that a GPU will actually draw something is it will read whatever is in the VRAM, the video RAM. So the GPU will read whatever is in like a little RAM chip, and then it'll display it to the screen. But meaning that, so when we're actually in this time period, so when like there are pixels being displayed to the screen, the GPU is the only thing that can read the VRAM. So the VRAM is 100% being used by the GPU when pixels are being drawn. But that kind of sucks, because what if the CPU wants to add or wants to like update a position of some pixel, or wants to like move something or change the color? So now the CPU does not have any access to the VRAM because the GPU is the one who's drawing everything. Yeah, so somehow we need to say, all right, GPU, like stop working for a little bit. We need to now hand the VRAM off to the CPU. And so now the CPU is able to update the VRAM. And then once the CPU is done, then we give it back to the GPU, and then the GPU goes and draws the next frame. Yeah. So, and the way that we do that is something called a vertical blanking area. So what actually ends up happening, and this is actually like how all monitors and how like HDMI and DVI and VGA, like all video signals work, is that for the majority of the time, so the GPU is actually working and it's drawing the image, and it's drawing it really awesome, going down the line, drawing everything. But then when it reaches the vertical blanking area, the GPU just stops working. And then so the GPU just stalls. And but the clock cycles are still going. And so basically what happens is that after every time we draw a frame, there's this little area where now the CPU can steal away the VRAM from the GPU. So yes, so here, so yeah, so in this area, which we call the visible area, the GPU is reading the VRAM. And then in this area, the GPU does not read the VRAM anymore, and now the CPU has access to the VRAM. And yeah, can anyone think of why we need to separate out the GPU and the CPU? Like, why can't they both talk to the VRAM at the same time? And there's a few reasons for this. But yeah, can anyone like put in the chat, or maybe like unmute and like give me a reason why we don't want them both accessing the VRAM at the same time? So yeah, imagine now that like the CPU wants to access address like 15, but so the CPU wants to access address 15, but the GPU wants to access address 16. So what's going to happen is now all of the address bits are probably going to be like ANDed or ORed together. So now all the address bits are ORed together. So now we're getting a completely different address. So then the GPU, so the VRAM now spits out some completely incorrect data. So the RAM is thinking, oh, okay, so I'm reading address, or the GPU is thinking, I'm reading address 16, but really it's reading some like random other address. And the CPU is reading and thinking that it's reading address 15, but really it's reading something completely different. So yeah, so data corruption or like junk values. And so what happens if the CPU is trying to access the VRAM at the same time as the GPU is you'll probably get like little like chunks of like noise. Like, yeah, let's say like we had no let's say like, yeah, we didn't protect the VRAM from being accessed by two things. We would see like anytime the CPU would access the VRAM, it would be noise and it would look like this. Overall, this is a big problem. And so what we need to do is we need to somehow avoid this. And yeah, so we avoid it by saying that in this area, the CPU just cannot access the VRAM. So that's what we say. We say the CPU cannot access the VRAM here. If it wants, it can access it here, or if it wants, like it doesn't need to. But all we say is that the VRAM, the CPU cannot touch the VRAM in this location. Yeah. However, so in an ideal world, what would be really cool? So in this area, so the CPU can access anything it wants, no restrictions. So what would be really cool is if we just say like, okay, actually, let's just like not even do anything with the CPU in this area. Let's only do stuff in the CPU with this area because like this is where the CPU can do anything. So, so like in an ideal world, you could do all of your game logic. Like you could start right here. You could do all your game logic, and then you would have time to like draw to the VRAM, and then you might have some extra time. So then it just like waits until like right here, and then it'll like go and start doing the logic for the next frame. However, that does not give us very much room because during the vertical blanking area, the vertical blanking area only takes up 1.43 milliseconds. However, the GPU has access to the VRAM for 15 milliseconds. So 15 versus 1. There's the very, very big difference between, really just, this is a really small amount of time. 1.43 milliseconds to do all the game logic, to draw all the different pixels and load everything to the VRAM. So this is very, very limited. So ideally, how the game code is laid out now, like as of like a few days ago, or maybe like last week, is now at the start of this area, there will be a function that's called do logic. So at the start of the visible area of the next frame, do logic is called. And the only restriction of do logic is that it cannot touch the VRAM at all. And then do logic will continue. And then when finally do logic is done, so when do logic is done, it will wait until the blanking area. So let's say like we end do logic right here. So then it'll wait. And then once it gets to the vertical blanking area, then it'll run fill VRAM. So these are your two main functions. So if you're writing JavaScript code, this is very important to understand. If you're writing assembly code, this is very important to understand. They're both called the same things. Do logic is where you put all of the game logic, like where you can update the positions of objects and classes and everything, maybe deal with collisions. But then in fill VRAM, that is where you put all of the VRAM stuff. So yes, so yeah, if you're doing like very little game logic, like overall, then you can just put everything in fill VRAM. But overall, it's better to like split them up because do logic has access to 183,000 clock cycles, whereas fill VRAM only has access to 17,000 clock cycles. So these are the two functions that you'll be like implementing. That's basically how you write a game. So you have two functions. You have do logic and you have fill VRAM. And every frame, do logic is run, and then the second that do logic is run, then fill VRAM is run. And then once all of that entire block finishes, then it will like move on to the next frame. And lag is handled in hardware, so don't worry if you end up taking up more than 183 clock cycles or more than 17,000 clock cycles, then it's all dealt with, and we'll just get like a frame skip, and it's not the end of the world. But the only thing that's just crucial is that you only ever touch the VRAM in this fill VRAM function, and in do logic, you cannot touch the VRAM. Okay, that is the summary of the drawing interrupts. Does anyone have any questions? I have not. Yes. Do logic. Well, so do logic doesn't necessarily run for 183 clock cycles. You can think of it that way, yes. However, really all the 183 clock cycles is actually just saying how long the visible area is. It has the ability to run for that, or it could go longer. Yeah, it can go longer, it can go shorter. Really just the visible area is 183 clock cycles. Yeah, really you don't have to even think about clock cycles. That's all handled in hardware. If you're writing game code, all you care about is just putting as much stuff in do logic as you can, and then trying to put only VRAM related stuff in fill VRAM. Really just don't even worry about clock cycles, just in order to optimize like performance, try to make do logic as fat as possible and try to make fill VRAM as small as possible.
So the do logic does everything except touch the VRAM, but what does it do? Does it like calculate the positions and whatnot, so then the like filling the VRAM is easier, or how does that work?
Exactly. Yeah, it's all up to you though. You can do whatever you want in do logic. Really, all of it, you can think of it as like pre-compilation before fill VRAM. Like fill VRAM is the actual stuff where like everything is actually updated on the screen. Do logic is all the calculations that you could do before. You're trying to do as many calculations as you possibly can before you actually have access to the fill VRAM.
Okay. Well, we could have the exact copy of VRAM, let's call it VRAM2, and then do logic fills VRAM2, and then during the 17,000 cycles, we just copy over.
Yeah, you absolutely could do that. I guess the one problem with that is that VRAM is like 2.2 kilobytes, and that's just quite a bit of memory. I guess yeah, and we'd actually have like plenty of time to fill all that. We could like copy it over. Like that's actually like how a lot of GPUs actually work, and that's called like the ping pong technique or something. But yeah.